Hello everyone. So I'm going to today walk through this understanding quadratic function exploration in where we're going to work towards developing what the A, B, and C parameters represent within a quadratic function. And to do that, we're going to take a closer look at this situation in which we're taking data from 1986 to took data and modeled it into a quadratic function. And in this particular quadratic function, t is the number of years since 2000, and p is the population of Arizona in thousands. And we have sort of a selection of data points from this function given in this table of values. And in looking at the table of values, we can quickly say that, generally the population is increasing since the year 2000, because it starts at around 5,112,000 people and increases up to 6,321,000 people. Now, according to this model, what was the population in the year 2000? So if I go right here to year 0, that's the year 2000, I can say, okay, well, the population was 5,112.35 thousand people. Or I could think of it as 5 million, so as a number that would be like 5,112,035 or 350 people. So that would be the sort of number written out. Now, where in the equation could I have found that information? So if I go back up to my equation, I should notice that this last number here is the same as that initial value in my table. So if I go that last number, that's represented with that C there. So where in the standard form equation, it's the C value. Now, if I want to say, well, will C always be the output coordinate of my vertical intercept? Well, the vertical intercept, a reminder, occurs when t equals 0. So it's basically the value of f of 0. So if I go back to my sort of standard form equation and I say, okay, well, if y equals ax squared plus bx plus c, and, when x equals 0, y, if I plug in 0 for all my x's, I would have a0 squared plus b0 plus c. Both of those 0 terms sort of go away to nothing, and I'm left with just c. So whenever I plug in 0 for x in a quadratic and standard form, I'm going to wind up with the point 0c. All right, so we've gotten the first parameter. Woohoo, we have figured out what c represents. So the next job is we're going to go take a closer look at the b value, that middle sort of term. And in this particular function, it's 130.68. Now to do this, we want to estimate the instantaneous rate of change at t equals 0. Now, if we remind ourselves, we can estimate the instantaneous rate of change by using the average rate of change. So an instantaneous rate of change is looking for the exact rate at a point in time. And without calculus, we can't do that. But we can get a pretty close estimate. So we just need to use our average rate of change. So a friendly reminder, average rate of change can be found by taking our change in output minus our change in input. Now, I want to find the instantaneous rate of change at time equals 0. So the temptation is to go up here to the table and go, well, I'll just go between 0 and 2 because I have those two numbers. But that's not going to get me a good estimate of what's happening at 0. I need to pick two time values that are really close to 0. So I would start with 0, obviously, and then I'm going to pick a number super close to 0. And so the next temptation is to be like 1. I'm going to use 1. Well, can I get closer to 0 than 1? So you might think 0.5. Can we get closer than 0.5? I like to take it at least a few decimal places over. I want an itty bitty number that's super close to 0. And so I'm going to be evaluating f of 0.001 minus f of 0 all over my change in x, which would just be 0.001. Now to do this, I'm going to go over to my Desmos calculator. And so you'll notice I've already typed in the function, and you can sort of see the graph here. But I can use Desmos and do some function notation here. So I'm going to type f of 0.001 and then minus f of 0. And then I'm going to take the whole thing and divide it by 0.001. And notice, so I end up with 30.679. So I'm going to go back to my work, and so this would end up equaling 130.679. And if I go back and I look at my quadratic equation up top, you should notice, my b value here is 130.68. That's just a rounded version of this number. If I had rounded to the nearest hundredth, I would have gotten 130.68. So where did I find this information? Well, it was my b value. And so what is b telling me in this context? It's telling me that in the year 2000, the population of Arizona was initially increasing at a rate of 130.68 thousand people per year. It's our initial rate of change of our quadratic function coming from that t equals 0 point. So I'm going to write that out. So the population of Arizona was increasing I'm going to add, initially at a rate of 130.68 thousand people per year. Remember, our rates of change should always have sort of two quantities. And so what is that b value telling us? We just talked about it. So the b value is giving us the instantaneous rate of change at x equals 0, at that initial vertical intercept point. All right, so we've gone through and looked at C and we've looked at B. So now we want to take a closer look at that A value. And A tends to be the hardest one to reach a conclusion of. But it's going to go back to sort of how the rates of change are changing. So the first thing that you're going to go through and do is you're going to actually find the average rate of change between each of these points. Now, unlike the previous example we looked at class, we do need to factor in that change in time, because if we notice, this is increasing by 2 every time. So this is +2 +2. So I can't just find the difference between my outputs. I need to also divide by my inputs. So I'm going to switch back over to my calculator. And so I'm going to go through and change out some numbers here, because why not reuse what I've already typed in? And I'm going to have f of 2 and then minus f of 0 with a change of 2. And I get 128.7. And I'm going to call that value A. We're going to show off some tips and tricks. Okay, and now I'm going to make this, oops, not A again. We're going to call this one B. And B is going to be the same thing. So we're going to have f of, but this time 4 minus f of 2. And we're going to divide that by, oops, too many. Divided by 2. Okay, and now I got 124.8. So I have first difference, and I can keep going. And so if I kept doing this, I would repeat this process for all the remaining values in the table. But to save us a little bit of time, I'm just going to fill them in. So we had 128.72, and keep in mind this is thousands of people per year. And so the next one was 124.8. And then if you kept going, you'd have gotten 120.88 and 116.96 and 113.04. So specifically, what does the rate of change on this interval right here tell me about the context of my problem? Well, it's telling me that the population increases at an average rate of about 124,000 people per year between the year 2002 and 2004. And generally looking at all those rates of change, I can see that the population is increasing. Just like we knew, we have positive rates of change. All right, now we want to find sort of this, almost, it's like the rate of the rate. So notice we're going to find the difference between our rates of change and then divide it by our change in time. So I'm going to do this for the very first box. And that's why I labeled this as A and B. So I'm going to do B, my rate of change between 4 and 2, minus A. And then I'm going to divide it by 2, and I get this negative 1.96. And so our rate of change, let's switch back to blue, is going up negative 1.96 thousands of people per year each year. So this is the rate at which the rate is changing. So thousands of people per year each year. And if I continued to do this, I'd find that all of those values come out as negative 1.96, which agrees with what we sort of know about quadratic functions, and that the rate of the rate should be a constant value. And so what this information is telling me is, since this is negative, I know that my rate is decreasing each year. And so I can be specific and say the rate of change is decreasing by 1.96 thousand per year each year. So we're not increasing by quite as much. So looking at these two things, I could say, okay, my function is increasing, but at a decreasing rate, which we talked about in class. Now, let's make that final conclusion, because we want to compare what we found, that value we found in that far column, that negative 1.96, with the A value here, negative 0.98. And you might be going, I don't see any connection. You know, but 8 times 2 is 16, and I have a 6 here. So what would I get if I go back to my Desmos graph and I did negative 0.98 and times it by 2? It's the same as the number we got in that rate of the rate column. And so if I take my A value and I times it by 2, I'm going to wind up with the sort of the rate of my rate of change. And I could look at this other context, this yogurt problem. We didn't do this in class, but you can look at the yogurt problem in one of the presentations online. And notice here, you could find out that the rate of the rate was 29.98 million pounds per year. And here we have an A value of 14.99. And again, if I take 14.99 and I times that by 2, guess what? I get 29.98. So that A value is going to help me figure out what the rate of change is changing by. So it's not just A in itself. I need 2 times A tells the rate of change. So it's going to tell us how the rate of change is changing. So that's going to help us know concavity. And so, so we can get a lot of information from that. All right, let's sum it up. And that's what this final question's asking us to do. Can we take all of the ideas from this exploration and put it into sort of 3 quick bullet points? This is great notes to our future forgetful self. This would be big ideas from the day on quadratics. All right, so if I look at what is C telling us, C is telling us in this particular context, the population at time 0. But I'm going to just write C in general is telling us the output at T equals 0. And in this case, that was the population at time 0. You could also think of it as our vertical intercept. That's a really helpful way. So C, output at T equals 0. B is the instantaneous rate of change at T equals 0. So this number is going to tell me, okay, from that sort of vertical intercept starting point, how is my function traveling? Is it going, up? Is it going down? What direction am I heading and how steep is it? And then from there, my A value is going to help me know how is that rate changing as we move, throughout our domain. So 2A is the rate of change. So how is the rate changing? So hopefully this sort of helps you make a little bit of sense of this exploration. Again, we're going to start class next time talking about some of these big ideas so that we can make sure we fully understand them before we move on to some other information. Looking forward to seeing you all soon.